Hello and welcome to lecture 26. So, in last lecture we were solving this numerical. We have done our calculation for different cycle parameters, which includes pressure and temperature calculation. We have done calculation for velocity components at the exit of the core engine nozzle and at the exit of the fan. Then we started doing the calculation for the performance parameters, which include thrust, thrust specific fuel consumption and different efficiencies like thermal efficiency, propulsive efficiency and overall efficiency. So, if we go through, this is what we have done in last lecture. Now, it is very important for this course to discuss the effect of different parameters on the performance. So, let us try to look at this chart properly. So, here in this case it says I can have different parameters which I can vary in the cycle. So, one of them it says like I can vary the fan pressure ratio, I can vary the compressor pressure ratio, we can vary what will be the turbine entry temperature. Same way we can vary what will be say our mass flow rate through this. So, all these parameters they are having their impact. So, if you recall when we were discussing about turbojet engine, there also we have discussed the effect of different parameters. So, let us try to look at what will be the impact of variation of these parameters on overall performance of the engine, because that is what will be helping designers to decide the parameters. Which parameters? Say like what need to be the fan pressure ratio, what need to be a compressor pressure ratio, what need to be say turbine entry temperature, what need to be the mass flow rate through the engine, and that is what will be deciding the expected performance in terms of thrust, in terms of thrust specific fuel consumption, in terms of different efficiencies. Let me put the point here. See, it depends on what is my application. Suppose if I am talking about the commercial aircraft, where these days people they are more focusing on the specific fuel consumption, or we can say fuel economy. When I am talking about application for the military engines, where people they do not bother of specific fuel consumption. This is just for the instant I am saying. Later on you will say now people they started talking about the specific fuel consumption importance for military engines also. Now, these engines we can also use for the application of say making of missiles, where my major concern is what will be the range of that missile, what will be the thrust capacity of that missile. So, it depends on what is my application, and that is what will be deciding what need to be the parameter. So, let us try to look at the performance parameters. We say our performance parameter as a thrust or specific thrust, thrust specific fuel consumption, air fuel ratio, propulsive efficiency, thermal efficiency, overall efficiency. Now, when we are talking about this turbofan engine, then it says it is depending on different parameters. Very first it says overall pressure ratio. So, we can say we are having compressing component as a fan. So, fan has its own pressure ratio. Since this is a numerical where we are considering only say single spool configuration, where we are not differentiating in terms of LP compressor and HP compressor. Suppose say it is 2 spool configuration, then we will be having LP compressor and HP compressor also coming into the picture. One more important parameter for say turbofan engine is bypass ratio. So, we will see what is the impact of this bypass ratio on overall performance. Next, what we have is turbine entry temperature, efficiencies. Here the efficiency of diffuser, fan, compressor, combustion chamber, turbine, nozzle. These efficiencies are also equally important, and if you recall, in second week we have discussed a lot about these efficiencies, and the research that is what is going on in terms of how to improve the efficiency of these components. let it be say diffuser, or we can say intake, maybe fan, compressor, combustion chamber, turbine, nozzle, all these components. Okay, that's what is a different ball game. That's what will be coming in a special component wise design. Here at this moment what we are discussing is the initial stage of development of the engine. Okay. Now, we have maybe ground condition or the flight condition. As I was telling, we have done the calculation for the ground condition, and today we will be discussing about the flight condition also. Okay. So, let us move here. So, this is what is our line diagram and our TS diagram. So, let us start discussion about the effect of fan pressure ratio. We will be putting compressor pressure ratio, turbine entry temperature, bypass ratio and mass flow rate to be constant. So, just realize the effect of variation of one parameter, that is what we are checking at this moment. Okay. So, very first thing we will see, that is say what is the effect of fan pressure ratio. So, here on x axis if we look at, we are increasing our pressure ratio. With increase of pressure ratio, here if you look at the thrust, that is what will be increasing. Now, this thrust, it is specifically I have plotted say hot thrust and cold thrust. Okay. So, let us try to realize this part. When I say I am increasing my fan pressure ratio, the meaning is in terms of my thrust equation, I will be having my exit velocity to be higher. Okay. And that is the reason why my cold thrust, that is what will be increasing with the fan pressure ratio. At the same time, what is happening for the hot thrust, with the increase of fan pressure ratio, the hot thrust, that is what will be decreasing, because that is what is getting infected by my V9 and fuel air ratio. Okay. So, you can say here in this case my exit velocity from the core engine, that is what is going to decrease. So, it is preferred that you just try with the calculation of this, that will give more clarity. Otherwise, it says like with increase of fan pressure ratio, my thrust is going to increase, but it is shown here separately for the clarity. Now, my specific thrust, we say it is represented in terms of thrust divided by my M fan plus M core. We can say that is what is my inlet air. It is increasing with my fan pressure ratio. This represents my design point. You can say this point where if I will be moving with the lower fan pressure ratio, the specific thrust is going to be decreased. Okay. Now, let us discuss about the fuel economy, what we say in terms of say thrust specific fuel consumption. Here in this case, we say when we are increasing our fan pressure ratio, our thrust is going to increase, and that is also impacting on my fuel amount of fuel, that is what we want to add. Just listen carefully what is happening when I am increasing my fan pressure ratio. You can say it required more amount of work, okay, for the compression, and that more amount of work we are getting from turbine. And for getting that more amount of work, you need to have your fuel input required, that will be higher. Okay. But when we are comparing this, it says my thrust number will be very high. Let us look at what is happening with the thermal efficiency. So, we can say my thermal efficiency, that is what will be increasing with the increase of fan pressure ratio. Okay. So, that is what is impacted by my fuel air ratio, that is getting impacted by my V9 and V10. Okay. The major contribution, that is what will be coming with V10 here. Okay. Now, let us look at what is happening with the effect of compressor ratio. Here fan pressure ratio, turbine entry temperature, bypass ratio and mass flow rate we are putting as a constant. So, can you please try to plot this, say maybe thrust versus compressor pressure ratio. Let us put say maybe hot thrust and cold thrust also. You will get surprised with the results here. it says like this is my plot. With increase of compressor pressure ratio, our thrust is going to increase, and that is what is say going to decrease with the very high pressure ratio. Be careful here, in this case we are putting our turbine entry temperature, that is what is fixed. Suppose if I say I am increasing my turbine entry temperature, with the increase of pressure ratio my thrust is going to increase. Okay. Very next we will be discussing about the turbine entry temperature, where you will get the feeling of this number. It says my cold thrust, since it is not being affecting on my say fan side, that is the reason why it is remains constant. And for hot thrust, it says with the increase of pressure ratio, you can say your fuel consumption will be increasing, and accordingly my V9 also is getting changed. And that is the reason why it says we will be having the variation of this hot thrust. In line to that, if we will be putting our specific thrust, that is what is majorly contributed in terms of thrust, because my mass flow rate that remains constant. Okay. Now, let us talk about say thrust specific fuel consumption, similar to what all we have discussed. Now, in order to increase my pressure ratio for the constant mass flow rate, and in order to achieve that turbine entry temperature, it is but obvious we need to have the specific fuel consumption that will be reducing with the increase of say compression pressure ratio. Okay. Now, let us look at with the thermal efficiency. This is what is similar to what all we have discussed for the fan configuration, variation of fan pressure ratio. Okay. So, it says like if we are increasing our pressure ratio both for compressor as well as for the fan, we are going to increase the thermal efficiency. Since this is my ground condition, so we are not having propulsive efficiency, we are not having overall efficiency. Okay. Now, let us look at the next parameter. It says my bypass ratio. What we know about bypass ratio? This is given by m dot fan by m dot core. So, when I say I am increasing my bypass ratio, the meaning is my fan mass flow rate is higher, okay, or we can say my core mass flow rate is lower. So, let us try to look at that. Here in this case we have taken my mass flow rate to be constant. So, in this case, since we are increasing our bypass ratio, means mass flow rate to my fan that will be higher, and that is the reason why you are having increase of thrust. At the same time, for the hot configuration or for the hot nozzle, with the increase of bypass ratio, my thrust is going to decrease. So, here we are having different trend. It says like if we are increasing the bypass ratio, my thrust is going to decrease. Again, I am telling you this is what is with the configuration of particular fan, compressor and turbine entry temperature, which are constant. It may be varying. If we will be talking about say increasing the turbine entry temperature, it will be giving me higher thrust in this configuration. Okay. Similarly, here in this case my specific thrust also is going to decrease, because my thrust is decreasing and my mass flow rate, that is what is constant here. Now, let us look at what is happening with the thrust specific fuel consumption. Any guess? Let us see. So, here in this case it says my thrust specific fuel consumption, that is what is going to be decreased with the increase of bypass ratio. Now, this is giving us idea about like selection of bypass ratio, where we are discussing about the thrust specific fuel consumption. Okay. So, our target is to reduce the thrust specific fuel consumption, but it should not be with the at the cost of decreased thrust. Be careful about that aspect. Okay. And here this is representing my thermal efficiency. For the lower bypass ratio, we will be having lower thermal efficiency. When we are increasing our bypass ratio, the thermal efficiency is going to increase. Okay. Now, let us look at what is happening with the turbine entry temperature. So, just try to plot this thing, and let us see what is your thought process and what is coming out. So, if I will be putting this, oh, here this is something different. Say my turbine entry temperature, that has nothing to do in terms of my cold thrust. Okay. Majorly what is happening is the change of hot thrust. Okay. So, if we are increasing the turbine entry temperature, we will be having hot thrust to be higher, and that is the reason my total thrust will come to be higher. Okay. When we are moving with the turbine entry temperature to be lower, it says something else. It says my hot thrust is going to decrease. So, this is indication for particular pressure ratio of fan and for particular pressure ratio of the compressor. If I will be going with the lower temperature, my thrust is going to be decreased. Okay. Same way here, this is representing the specific thrust, and the case for thrust specific fuel consumption, that is what is showing a different trend what all we have seen earlier. Here in this case, with the increase of turbine entry temperature, you can say in order to achieve the turbine entry temperature, you need to add more amount of fuel, and that is the reason why the thrust specific fuel consumption is going to be increased. Okay. So, maybe you may need to go with the optimization in terms of thrust specific fuel consumption, then you need to play with all these parameters. Okay. We are not discussing anything about the optimization, but this is what will give you idea how you will be deciding the numbers. Okay. Now, let us look at what is happening with the efficiency. It says with increase of turbine entry temperature, the thermal efficiency is going to be decreased. This is related with what we say in terms of the amount of fuel what we are injecting. So, it says if we are having the target of increasing the turbine entry temperature, so somewhere you need to compromise for particular fan and compressor pressure ratio in terms of fuel consumption. Okay. Now, with this, let us see what is happening if we will be changing our mass flow rate, putting all other parameters to be constant. So, for that case, for both hot thrust and cold thrust, this number is coming same. We are having thrust, that is what will be increased with the increase of mass flow rate. Similarly, the thrust specific fuel consumption, that remains constant, and here if we look at, this is representing what will be my nozzle area. So, for both the cases, if we are going to increase the mass flow rate, it is but obvious, it is direct proportion with the area, and that is the reason why my area will be increasing. So, my exit area of fan nozzle and exit area of cold nozzle, that will be higher. Okay. And this is representing the thermal efficiency point. Okay. So, maybe in order to increase the thrust, it says you can go with the increase of mass flow rate, but somewhere you need to compromise in terms of fuel consumption and in terms of efficiency. Maybe in order to handle that, you need to have larger size engine, maybe entry diameter need to be larger, and at the same time maybe exit dimension also need to be larger. So, that is what will be deciding the mass flow rate parameter. Now, this is giving idea about our ground condition. So, let us take a numerical, same information, same data what all we have used for the earlier numerical, but here in this case we are changing in terms of my flight condition. It says my flight altitude is 33,000 feet, my flying Mach number is 0.9, the temperature and pressure at that particular altitude is 222 Kelvin, and P infinity is 26.2 kilopascal. So, let us try to solve this numerical. So, that is what will be giving us feeling the same engine when it is flying at particular altitude, what will be the performance, and that is what we need to check with, and then we will try to compare what is happening when it is at the ground condition and what is happening when it is at the flying condition, and that flying condition is at particular Mach number. Okay. So, similarly, what all we have done in order to solve this numerical, we will be dividing our components. Very first component will say intake or the diffuser. For that, we have information about the temperature and pressure recovery factor. It is given m infinity, that is my flight Mach number, that is also given. So, that will help us in order to calculate what will be the exit pressure and exit temperature from the intake. Same way for the fan, we will be calculating what will be the exit temperature and exit pressure from the fan. We have our next component as a compressor. For that compressor, we know what is the efficiency and pressure ratio. So, we can calculate what will be the exit pressure and exit temperature from the compressor. Since this is single spool configuration, we have next component as a combustion chamber. For this combustion chamber, we know what is our pressure drop and maximum turbine entry temperature. We know what is the calorific value of this fuel, and based on that we will be calculating what will be the exit pressure and fuel air ratio. The component we have next is say turbine, and for turbine we are given with say efficiency, we are given with the mass flow rate, and based on that we will be calculating our exit pressure and exit temperature. The component we have next is tailpipe, and for that tailpipe some pressure drop value it is given. So, based on that we will be calculating our exit pressure and exit temperature from the tailpipe. Then we have our turbine nozzle. For that turbine nozzle we will be doing the calculation called the critical pressure. Then we will be comparing that critical pressure with the atmospheric pressure. Based on that we will be calculating what will be the static temperature, what will be my exit velocity. Similarly, for the fan also we can do the similar calculation, and we will be calculating what will be the exit velocity from the fan nozzle. Once we have all these parameters, we can calculate what will be the performance parameter of this particular engine. And this performance parameter we say they are say thrust specific fuel consumption, and all three efficiencies. Okay. So, I am sure you have now idea, and you can make this diagram, you can start doing the calculation for this. So, let us put this is representing my line diagram and TS diagram. So, let us look at very first component. What we have is our inlet diffuser or the duct. Again, as we have done for our earlier numerical, we are given with the diffuser pressure recovery factor is 0.98, that is nothing but the pressure ratio, total pressure ratio. We can say it is P02 by P0 infinity. That means we need to have what is my entry total pressure. Now, in order to calculate that entry total pressure, we need to go with say isentropic relation. So, here in this case, this process I say infinity to 2. Since here the m infinity value is given 0.9. So, we can calculate our velocity. This velocity is coming to be 268.8 meter per second. We can do the calculation for P0 infinity, since this Mach number is known to us. So, if we will be putting this number, it says my P0 infinity is 44.31 kilopascal. So, in previous numerical we were having our m infinity that was 0. So, be careful in terms of doing the calculation. Okay. Now, what is the next case is to calculate our exit pressure. So, this exit pressure we have it is 0.98 into 44.31. It says my exit pressure to be 43.43 kilopascal. Okay. Now, this is my exit pressure from the intake. I can do calculation for the exit temperature. This exit temperature we can correlate with the static temperature in terms of say Mach number. So, if we will be putting this number, the inlet exit pressure or intake exit temperature is coming say 257.96 Kelvin. So, I am sure you are aware of. So, here if you are making mistake in terms of doing the calculation, and if you forget to put this Mach number, the whole pressure, temperature at the exit of your intake will be wrong. That means all your cycle parameters will go wrong, and that is what will be giving you wrong value of exit velocity. Maybe your nozzle in actual condition is choke, while doing your calculation it may come unchoke. So, what thrust calculation you will be doing, that also will go wrong, thrust specific fuel consumption also will go wrong, your efficiency values also will go wrong. So, be careful when you are doing your calculation and what parameter it is given. Is it diffuser efficiency, diffuser pressure recovery factor, or say total pressure ratio? Read the information carefully and do this calculation. Okay. Now, let us move towards say next component we have, it is our fan pressure ratio. Since my fan pressure ratio is given as 2, so from that we can calculate our exit pressure. This exit pressure is 86.86 kilopascal. Now, we have information about say temperature ratio. We know our temperature ratio, it is a function of pressure ratio and efficiency. So, since we are given with the efficiency of 90% and fan pressure ratio is 2, so exit temperature is coming 320.73 Kelvin. Okay. Now, very next component what we have is our compressor, and for compressor we are given with the compression ratio of 8. Our say entry pressure, that is what is say exit pressure from the fan, be careful, that is 86.86 kilopascal. So, let us put this number, that is giving us say compressor exit pressure to be 694.88 kilopascal. Similarly, we can do calculation for our temperature ratio based on what will be our compressor pressure ratio and compressor efficiency. So, let us put this number, say compressor efficiency is given 88% and compressor pressure ratio is given 8. So, from that we will get the exit temperature as 616.47 Kelvin. Okay. Now, what component next we have is our combustion chamber, and it is given there is a drop of 3% pressure in combustion chamber. So, the exit pressure from the combustion chamber, that is given by 0.97 into 694.88. It says the exit pressure is 674.03 kilopascal. Okay. Now, we are interested in temperature, but this temperature it is given, turbine entry temperature is given to us. But what is our main important parameter? The parameter here is fuel air ratio. Okay. So, let us try to calculate that fuel air ratio. So, we can write down our mass balance. So, this is what we can write down in terms of mass balance. This mass balance is important sometimes in spite of given like number as say turbine entry temperature, maybe fuel consumption in kg per second. Suppose say that value is given, my core mass flow rate is known to me. So, based on that we can calculate what will be the exit mass flow rate. So, read the information carefully. Okay. Now, we know in order to calculate the fuel air ratio, we will be going with say energy balance. So, this energy balance we can say heat input, it is in terms of m dot core H03, and this is mf into Cv into your burner efficiency. My exit will be m dot core plus mf into H04. So, if we are putting this number, my fuel air ratio is coming to be 0.0252. Okay. Again, let me repeat here, be careful what units we are putting for Cp, it should be in joule per kg Kelvin. Same way calorific value also you need to put in terms of joule per kg. If you are making mistake here, then it will give you wrong value of fuel air ratio. Okay. Now, the component what we have is our turbine, and for this turbine we are writing my turbine work, that is what will be balanced by compressor work and fan work. Here in this case nothing is mentioned in terms of efficiency. So, we will not be putting any mechanical efficiency term. So, let us put the balance here. So, here this is representing my turbine work and this is representing my compressor work plus fan work, and if you will be putting the number on simplification, this will give the exit temperature from the turbine as 989.52 Kelvin. This mass balance, energy balance, work balance, these terminologies are very important. Okay. If you are making mistake, then there are highly chances that we will be going into soup. Okay. So, be careful about this formulation. Okay. Now, let us move towards the calculation for what will be our exit pressure from the turbine. This exit pressure we are correlating in terms of say our turbine efficiency. So, if we are putting this, my exit pressure we can say it is coming to be 133.39 kilopascal. It is preferred when you are sitting for this class, you just sit with pen, paper and calculator, so that you will verify the answers also, and that will give the confidence. Okay. Now, what next we have is in terms of my tailpipe, where we are having drop of pressure, and this drop of pressure is 2%. So, if we are calculating our exit pressure from the tailpipe, it is 130.72 kilopascal. So, what all information given to you, read it carefully. Suppose this 2% if I will not be taking, then my pressure at the entry of the nozzle will be different, and that is what will be reflecting somewhere in terms of calculation. Okay. So, be careful about this calculation also. Now, what we have next, it is the temperature. So, my process within the tailpipe, it is adiabatic process. So, the exit temperature will be 989.52 Kelvin. Okay. Now, let us do the calculation for the turbine nozzle. Very first thing we will be doing is to do the calculation for critical pressure. This critical pressure we are correlating in terms of say nozzle efficiency and gamma value or specific heat ratio. If we are putting this number, we will be getting the critical pressure, and this critical pressure is coming 68.93 kilopascal. Now, let us compare this. What it says, since this critical pressure is greater than that of our atmospheric pressure, that is the reason why my turbine nozzle is a choke nozzle. When it is say choke nozzle, we will say our exit pressure will be equal to critical pressure, and that is 68.93 kilopascal. Okay. You need to be very careful in terms of doing this calculation here, because your small mistake and your thrust calculation will go wrong. Okay. Now, what next we need to do is to calculate what will be the static temperature from this core nozzle, and that is given by gamma plus 1 by 2. The static temperature, if you will calculate, it is 860.45 Kelvin. Since this nozzle is choke nozzle, so nozzle exit velocity will be given by gamma into R into T9. So, here this will be square root of 1.3, 287 and 860.45. That says my exit velocity from the turbine nozzle will be 566.6 meter per second. Okay. Similarly, we can do the calculation for our fan nozzle. So, formulation will remain same. Be careful, this will be given in terms of my entry pressure divided by critical pressure, and if we will do this calculation for the critical pressure, this critical pressure is coming to be 44.22 kilopascal. So, let us compare this pressure. This pressure is coming to be greater than that of our atmospheric pressure. Okay. And that means, here my nozzle is a choke nozzle, and for this choke nozzle my exit pressure will be equal to critical pressure. Okay. Same way as we have done the calculation for our turbine nozzle, we can do the calculation for the static pressure from the fan nozzle. So, let us put these numbers. If we are putting this number, my static temperature from the fan nozzle is 267.28 Kelvin, and if you will be putting this, it says my fan exhaust velocity, that is coming to be 327.7 meter per second. Okay. So, these numbers they are comparable now, V9 and V10. We will see what is the impact of this. Now, once we have this calculation, our next requirement it is to calculate what will be the area, and this area we are calculating based on our continuity equation. So, for turbine nozzle my mass flow rate is given by m dot core into 1 plus f. Since in this equation density it is unknown, but we know from perfect gas equation rho 9 it is P 9 by R T 9. So, let us put the static pressure and static temperature. It gives the static density as 0.279 kg per meter cube, and the exit area is coming to be 0.0973 meter square. Similarly, we can do the calculation for our exit area of fan nozzle. For that, we need to have what will be the mass flow rate from this nozzle, and this mass flow rate it is given by beta into m dot core. This beta is given, it is 2 into 15, and that is what is giving 30 kg per second. Let us put this number. It says my area it is given by m dot divided by V 10 into density, and that is what will be giving me the density as P 10 by R T 10. So, my static pressure and temperature from the exit of the fan nozzle they are known to us. If we will put this number, this density is coming 0.576 kg per meter cube, and based on that we will be calculating our exit area, and this exit area is coming 0.1588 meter square. Okay. So, here we are stopping with. In this numerical we have discussed about the flying condition, and we have observed like the initial calculation for the intake, that is what will be different, because Mach number effect, total pressure recovery factor, those all have their own impact. We have done the calculation for different cycle parameters at the exit of different components. We have done the calculation for the exit velocity both from say fan nozzle as well as from the core engine nozzle, and we have done the calculation for the area. Now, in next lecture we will be discussing about the performance parameters, and once we will do the performance parameter calculation, we will be discussing the effect of different parameters, cycle parameters on the performance. And let us try to discuss this comparison both for the flying condition as well as for the ground condition. So, that will give more clarity in terms of understanding this cycle analysis for single spool configuration. Thank you very much.